Hello and welcome again to my Physical Science Online video supplement series. Today's video is going to be a lab walkthrough video. Specifically, what we want to do is look at the spring oscillator lab, which is also being used this semester as our formal lab reports lab. We are required to basically collect formal lab reports from every general studies lab course, and so now we are designating this lab as the lab in which the formal lab report will be collected. The Spring Oscillations lab basically is a follow-up to two of the other labs that you've already done this semester. First of all, you have your lab building a spring scale, which you did during the third week of the term. And for this term, you did this lab using basically a spring that you found that was about a foot long, and then using a water bottle and bucket or pail or coffee can or what have you in order to produce the masses. And so this was what we call a Hooke's law lab, the law that governs how much force a spring will exert versus how much it's been stretched or compressed is called Hooke's law. And so that was what this lab was about. And then last week you did the pendulum lab. And in the pendulum lab, you were supposed to basically determine what it is that affects the period for a pendulum oscillator. So now this week we're looking at a different type of oscillator, a spring oscillator, or a mass on a spring oscillator. And because I'm in kind of a smaller space here with this camera, I'm not trying to duplicate the spring that you use and the masses that you used for the Hooke's law, but you should already have a spring and some mass system for Hooke's law in place, and I would suggest that you just use what you used for that week so you don't have to go track down another spring and all that. Plus, you should already know what the spring force constant is for your existing spring. Now, you may still have to repeat this process a second time because your spring, one of the things you want to be able to change in this week's lab, the Spring Oscillations lab, is how the period of oscillation depends upon the spring constant. Now, for the sake of doing this lab this week in this small space that I have set up to make this recording, I am not using the same springs that were recommended for you for the Hooke's law lab. Instead, I have a different set of springs that I obtained actually from online. This is actually 3 different springs. I'll even put up what I got and where. It's basically these, I guess this is called ISCO Labs Hooke's law spring, and it came as a set of 3 springs. There's basically a shorter one and 2 longer ones, and of the 2 longer ones, one is a relatively stiff spring and the other is a relatively loose spring. You can see that one of them is a little sort of floppier than the other. And then also to help me with this demonstration, I have just a little stand that I can hang the spring from. So here's the spring. It's now attached to this stand like so, and I'll try to bring it up a little closer to the camera, I think about there. And then instead of using water, I have a different mass set. These are basically just little washers, like what you put on the end of a bolt. Okay, and so you are free to order these, order these springs and use them if you'd like instead of what you had before. Uh, they are $8.50 as of the making of this video. Obviously, prices change. And when I ordered them, I don't know that I had prime shipping. Basically, I ordered them through the university. They arrived about a week after they were ordered. Okay, so that was what my delivery time was. Your mileage may, of course, vary. And again, please do use what you already have if you have it, um, because I think it will be easier for you to just use the spring that you already got from the previous experiment. All right, so and then the other thing about these little washers is why I'm using them is because they're pretty easy for me to work with. I just have a little string like this and then a washer, and I essentially can thread the string through the washer, and if I want a little more mass I can thread it through several of these washers, and now this is basically the weight that I'm going to be hanging from the end of the spring. So let's see if I can get them attached in some way to this spring. Okay, so then we hook it on like this. You should be able to see it. I'm actually going to move the camera to a different angle. Alright, so now we see the mass attached to the spring set, sitting here on my table. Basically what you do at this point is you pull the little masses down by some additional displacement. You can see that the spring is somewhat stretched from its initial length. This is actually another spring whose length unstretched is the same as the length of this one unstretched. And you can see I'm holding them next to each other, that this one that has weights on it is in fact stretched and everything. What you want to be able to do here, if we pull back open the instructions, is you're basically going to be testing out, does the initial displacement affect the period, does the mass affect the period, and does the spring's stiffness affect the period? Okay, so you'll recall from last week's experiment with the pendulum that period of oscillation is the time required to complete one oscillation. So if I pull this thing down and release, it should bounce up and then bounce back down and kind of do a motion like this. And so for a spring, one complete oscillation, if I pull down and release, if I pull it down and release, it goes up, it comes back down, and that's one oscillation. 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. They're pretty fast on this particular spring, but if I choose the other spring, here, I can pull them down and release, and it's not quite so fast. This is actually the same amount of weight as the previous. So 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. All right. So you are trying to determine what the period of oscillation is for the mass at the end of the spring, and you're going to want to do that for different values of the initial displacement. So like so, I'm actually trying to hold so it doesn't bounce around quite so much, because you really just want an up and down motion like this, not the bouncy thing that we had before. And it has, my setup has a proclivity to be bouncy. Hopefully you don't have that particular issue. It's not a big issue, but it does make it a little harder to time, especially if there's a large scale motion to it. Okay, so I can pull down by more and I can pull down by less. So here is equilibrium right here. I can pull down like this, that's some amount of displacement. I can pull down like this, that's more displacement. So one question might be, which for which of these two displacements is the period longer? The relatively short displacement like this, or the longer displacement like this? And one thing that I should add here, this isn't, it is maybe a little bit safety, but it's mostly just experiment success or non-success. Here's how high this thing would be if the spring is totally unstretched. Okay. Here's how high it is at equilibrium. Okay, so just resting here, the spring has stretched by the difference in these two heights. If I pull down by more than that amount, like if I pull down all the way down to here and release, this thing goes crazy. It may actually fly off of the spring holder and so on. So you just want to be sure that when you pull down, it's by less than the amount than what the spring has already stretched by. And so that's also another way of saying that you may want to use enough weight that your spring actually stretches a substantial amount so that you can try short and long. Okay, so now going back to the screen itself and what our instructions are, there's a bunch of background information that kind of hopefully reminds you of what we did in the pendulum lab from week 5, the spring lab from week 3. Reminds you of Hooke's law and what the result of Hooke's law should be. Reminds you that you can find a frequency. That frequency is the number of oscillations per unit time. You're looking here for period, which is how much time to make one oscillation. So bear those things in mind. Okay, so let's turn mostly to the essentially the instructions themselves. You're given a bunch of basic instructions here, and the reason why the instructions are a little more basic than normal is because you are going to be required to write up a procedure statement as part of this formal lab. That's also why these videos for this week are a little more simple and basic than for most other weeks. Essentially, I have to read your procedure statement and evaluate it. And if I tell you step by step what the procedure is in the handout and in this video and so on, then we end up with essentially two very likely possibilities, both of which are bad. One is you just copy word for word the procedure statement, in which case that's kind of plagiarism, and we don't want that. Or two, you modify it heavily from what you're supposed to do, in which case your procedure statement ends up just kind of being wrong. So the instructions this time around are more like, here are your goals and here are some ideas for attaining those goals. Preliminary, you want to take your spring, again, this guy right here, or your version of this guy, suspend it, hang some known amount of mass on this. And in case you're wondering, is this a known amount of mass? Well, for me, I'm set up so that I have a little scale here that I can use to basically like weigh out each of these washers. And so if I turn on the scale and put a washer on it, this washer is 7 grams. If I put a second washer on it, now we're at 13.8 grams. They're not all exactly the same, but they should be pretty close. 3 washers worth, we're at 20.8 grams. So they're basically about 7 grams or maybe slightly less each. Okay, and so then basically I go from here and I look at how many have I hung from here, and it's 1, 2, 3, 4, 5, 6, 7. So I basically have about 59 grams hung from this spring. And I could weigh it out beforehand, again using this little scale. For you, if you are using the same equipment from week 3, then you know that you can basically get the mass by essentially like adding some water to a jug. And as long as your jug is, or can, or whatever you're holding it in, is much, much less than the mass of the water, then it can be more or less neglected and you'll get reasonably accurate results. So if you're using a milk jug that has a mass on the order of like 20 or 30 grams, then just be sure to add about 300 grams worth of water to it. Just like I'm not counting the mass of the string in my 50 grams here, because the string is less than 1 gram, and so I have many times more mass here than I do here. Okay, if your spring is a foot long, and that's the instructions from the lecture set 3. If your spring is 1 foot long, then you should add basically enough mass that it stretches out by about 5 to 10 centimeters. Okay, that's about 2 to 4 inches. So instead of being 12 inches long, your spring should now be like, say, 15 inches plus or minus 1, like 14, 15, or 15 or 16 inches long. Okay. Then from there, you have to pull down by some additional amount. Maybe you decide to pull down by an additional 2 centimeters. Okay, so focusing here again, this is equilibrium. I maybe want to pull down another 2 centimeters, so I pull down like this to release. Okay, I think that the easiest thing to say you have here is if I pull down by 2 centimeters and I use 7 of these, or in your case maybe like 100 or 200 milliliters or whatever, and I use this particular spring, those are sort of like my controls for the experiment. Those are my, let's say that those are my base values, okay? And so if I change how much I pull down by, then I need to A, be using the same spring, but also B, be using the same mass whenever I make this change. In other words, make one change at a time, and all other parameters should be like what we have already present. Okay. You are testing, you have 3 things that you can test here. The first 2 should be the relatively easy ones, your initial displacement and your mass. Okay. So for initial displacement, that basically means keep the mass the same, keep the spring the same, change how much you're pulling down by. All right. So pull down by 2 centimeters, release it, time it. Pull down by 4, release it, time it. Pull down by 8, etc. Pull down by 6. And you're supposed to get 7 different displacement values, and you're supposed to do 10 complete oscillations. Okay, so to give some idea of what this experiment would in this case look like, you need to have for yourself a timer and then this spring and mass system. Alright, so here's my masses, here's my spring. I pull down by some amount and I release. And then what you want to do, I've got on here my cell phone with the stopwatch function on it. Okay, so I go to stopwatch function. Essentially what I do is I want to pull down and then release and time it. And I'm going to actually move the spring up a little bit so I get a little more space to work with. Um, so we pull down and then release, and you want to time for 10 oscillations. So ready and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and then you get a time on your timer. So the time that I just happened to have obtained here is 6.45 seconds. Okay, so now basically what we want to do is make a calculation for this. And what I'm going to do here, I'm going to go ahead and open up a spreadsheet for this calculation. I'll show you pen and paper, but I'll also show you how I'm doing it on the spreadsheet. So you'd maybe have like one category for mass in grams, okay, and then another category for time, 10 oscillations. So let's type that in there. And then that should be in seconds. Then you can get the period, which is also in seconds. And lastly, um, you really want the mass to be in kilograms. So this one right here, I changed out springs. So this one is 21 grams. So I type 21 here. I type in my 6.45 seconds. My period should be that number divided by 10. Okay, and then my mass is actually the mass in grams converted into kilograms. So divide by 1,000. All right, so maybe I now do a different mass, for example. Okay, so let me add a little more mass here, or take a little mass off. Okay, so again, we set up the spring, we set up our stopwatch. This time I now have only two masses on here, so this is like 14 grams worth. So we'll enter that in a sec. Again, I pulled down here by about this much the last time. There's actually, you can't see it because it's facing me, but there's a little built-in ruler here that I'm using to measure that I'm pulling down by the same amount. Oops. So we go ready, set, release. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and this time I got a slightly different time on here. It is 5.33 seconds. Okay, so this was again 14 grams. This is 5.33 seconds. And so I would maybe keep adding more mass to it and repeating to see if this is a fluke or just a weird reaction time or whatever. Okay, and so that actually goes with essentially these instructions. So you're supposed to ultimately get 7 data points, so 7 different choices of mass. Once you have your 7 data points, and I do not, but maybe presumably I just keep adding another one, so we'd have like 28, 35, 42, 49, 56, something like this, and then we'd have our times in here. What you would do next is you would want to insert a graph. Okay, and so what we do is, okay, so what I do is I say insert chart. I go on here. What I want is an XY scatter plot. Here's my XY scatter plot. Go to data series. We add a series. Basically, we need to name the series, which I'll do in a moment, but you want to get your X values, which in this case are the masses, and then the y values, which in this case is the period, and I accidentally selected the wrong set of masses. It's actually this set of masses, or these masses. Okay, and so then you need to name your graph. So I'm just going to put a name there momentarily. For now, it will just say column D. Okay, and then ultimately you're going to do this for all three springs. So you'd have two more series with these data. They don't have to have the exact same mass in them. Or at least I would have two more series. You probably one more series. And how you can do that one more series is if you take a spring, whatever spring you used before, and sort of let's focus it on this guy again. Like here is the unstretched spring. If you were to rig it so that only this bottom part can stretch, I don't know how well you see this from this angle, so I'm going to move over here. Basically, what we have is I'm holding part of the spring so that it cannot stretch, the other part can. Okay, and if I then repeat this experiment by basically just holding this stuff in place, pulling down, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, timing it, basically only half of your spring is actually being allowed to stretch, and it means that you're going to have a different spring constant for your spring than if your whole spring can stretch. Okay, and so that basically goes with, in these instructions, the spring force constant part. Basically you just make it so that the spring cannot all stretch. And you could do that by holding it like I showed you. You could also do it by cutting your spring. Like if you got some wire snippers, you could cut the spring in half. Just know that once you've done that, you can't, reuse it necessarily. And you'll want to measure the new spring constant. And so if you haven't already done that, well, you were supposed to have in the lab 3, and so I actually did this for all three springs. I end up with a graph that basically looks like this graph that's shown here. And you'll notice that when all is said and done, this graph has a title on it. This graph has axes that both have scales. They both are labeled. So this is a force axis. These are the units, newtons. This is the scale. This is a stretch from equilibrium axis. These are the scale. This should actually have a unit to it, so we can just add onto it. Unit is in meters. There is a little key to the side. Blue square represents the short spring. So basically this shorter spring that came in the set that I got. The red square is the longer but looser spring, this one right here. And then this one right here is the yellow triangles. So red diamonds, yellow triangles. Okay, and that's all shown on this graph. You might want to, if you want to kind of pretty it up a little bit, you can tell it to insert a major grid like so, or you can say to remove the grids. For example, if you have equations displayed on the graph and you want those to be a little easier, you just go in here and essentially say delete the major grid, and then then here for the y-axis, delete the major grid, and now it's nice blank space in the background. Okay, where these came from, if I come over here back to this newer graph that I'm making, you basically click on the data. I'm right clicking on it on my Windows computer, and what I'm doing is I go insert, not data labels, that's not what I wanted. I want to insert a trend line. Okay, and then click this button right here that says show equation, and it will show you an equation on the graph. You can also format it after you've added it. Like if I wanted to have extrapolate backwards so that I see where the intercept is, do that. Now it's extrapolated backward. Obviously I didn't put a title on this one. You would basically need to add that when you're setting the graph up initially. In the area you can change colors and whatnot. That part's not terribly important. And you'd obviously want to put in the labels like what I have over here with these right here. Okay, and you can do all that if we start over on this graph again by basically going insert chart. My program's a little silly. I have to kind of move over so that it's not showing the data because otherwise it becomes hard to select. I am using an XY scatter plot, points only. I am selecting data, adding a series. You can add a name for the series by having something here like short spring or something like that, or full length spring. Select the X values, so I wanted to put mass on the X axis. Select the Y values, that's going to be my period. And then if you hit next, you can add in a title, so like period versus mass for 2 springs or something like that. X-axis, you'd say mass because that's what's on there. Units are kilograms. Y-axis is period, so you'd type like period, put the correct units, which are seconds, hit finish. Column D, maybe we'd say like short spring. So now it says short spring in here. That's basically the process for making this graph for you. This program that I'm using is LibreOffice Calc. You can also use Microsoft Excel. It'll work more or less the same. Maybe a few slight differences, but it'll work out. You can also use some other program if you want. I think a lot of people like to use some online graphing tools, which are fine. Okay. You are ultimately changing in turn the initial displacement, the mass, and then the spring constant. Okay, so do all 3 of those things. Make a graph that has this for your full length spring. Make a graph that has this for your full length spring. Modify your spring so it's not full length. And then you can basically either choose to make a third graph that has one mass on it and different, here's my half length, here's my quarter length, here's my eighth length, or whatever. But bear in mind that you'll have to go back and do Hooke's law to get the spring constant each time you do that. Or for whichever of these graphs you actually see substantial change in, like if this one you're getting substantial change in, you can plot 2 plots on here, one at full length and one at half length, to show whether or not spring constant actually does affect the period or not. Okay, so that's sort of like the experimental procedure. There's some lab report considerations in here. Remember that your data may not make a straight line. It may actually be curved. So you may have to therefore go through some linearization process. In this case, you do it by squaring all the values on the x-axis. Now that I've closed that program I had open, let's reopen it again, and For example, maybe it turns out that the looking at this that I have something like this. Like, let's say I fill these down, and maybe I don't have these data as such, even though these are the data I record. Maybe I use a different spring, and I happen to get like, um, uh, say, like 1 here, and then this one might be like 1.4, and etc. So this one maybe is like 1.7. This one maybe is like a 2. This one right here, um, etc., etc., etc. Okay, so 2.2, uh, 2.3, 2.35, something like that. Okay, so you can see that this is not a very linear graph. And so you can try to linearize it. This is not going to make a perfect line because this is not data that should make a perfect line. But like, come over here, and let's say we decide to square all the periods. So we'd maybe label this one as like period squared. And so you'd basically just say like this column squared, and then do that for each one of these. Okay, and then you would need to make another graph. I may actually be able to get away with just copying this graph and pasting it. Sometimes the program will let you do that pretty nicely, and sometimes it won't. Then what we want to do here is go to the data ranges, and then essentially I've changed my y values while keeping my x values the same. So I would select my new y values, and then that will change what the data looks like. Okay, and we ask, is it linear now? And like this right here is not still a perfect line, but it's more obviously linear than this one was. And for a more realistic set of data, something like maybe these data instead, you can see still that this is not a linear graph. And then again, I have just done the same thing where I just squared all of these values and then replotted, but now this versus this instead of this versus this. Okay, and now you see that this makes a very nice straight line. I can go in, I can add my trend line. Maybe I extrapolate it backwards by however much, by like 14 grams or 0.014 grams backwards, so it goes through the origin. Maybe I go down here and insist on making the scale for the axis also show me the origin. Okay, so I can like force to show where the origin would be on this. You see that this is now linear. So this would be equivalent to this linearization data that you have here. Okay, so I do expect you to do something like this. If on the other hand you have a like a constant, so pull this thing back up, maybe it turns out that instead of having something like this, you get like 1, 1.01, 1.02, 0.99, say 1 again, 1.02, 0.97, something like this. Like, this doesn't look very much like anything in particular, but the scale has been changed. And so for this one right here, again, you may have to format your axis, and then you really want it to run from the origin to whatever values you're showing. This right here credibly looks like it could be a horizontal line, and so we would not in fact have this second column. We would just simply have a horizontal line like this, and we'd say there's no relationship between period and this. And it looks like I made a little typo here. But that just still looks more or less like it could be along a horizontal line. In fact, it goes along this horizontal line that's already present for me. Okay, so that's one bit of your considerations. There's this stuff right here is pertinent to the formal lab instruction. Again, like, remember that if you go into your course online, here's home, we go over to modules, and then you have this formal lab report guidelines PDF. Okay, and so like open this up and look through it. All right, so the basic guidelines for it, and I've just pulled it up as a standalone PDF. It tells you when you're writing this lab up, I want your lab report to be typed up font size 12 using one of these three fonts, Arial, Times New Roman, or Calibri. I want it to be double spaced except for captions around figures and tables, which can be single spaced. Obviously, you're taking this course online, so you don't likely have any co-authors or lab partners on this. They did require that this assignment, this thing, be the same for online and on class. So for some people, they're doing it on campus, and therefore they do have lab partners, and would have to put those people's names on it. It's the same. Everybody gets the same document of this to look at, and then this walks you through what's actually expected of the document itself. So you do an introduction, should be concise, kind of like my videos aren't. But basically just talk about the experiment, put it in context. Look, we've done 2 other experiments this semester that are similar to this one in some way, so you might mention those as part of your introduction and background. You should be making any kind of scientifically supported theory prediction in this section. So coming back to your handout, if you look on here, like, I've given you this whole background information statement. Among other things, you have an equation for frequency in terms of the spring constant K and the mass M. The frequency is the number of oscillations per unit time. The period is the amount of time to make an oscillation. So I expect you to maybe put these things together to make a prediction that says something along the lines of, like, the period should depend upon, let's say, the mass and initial displacement, but not upon the spring constant, or the period should depend only upon the mass, or it should depend upon mass and spring constant, but not initial displacement, stuff like that. Like, some statement of that form should be clearly made towards the end of your introduction. You should probably also follow that up with an actual quantitative statement. Like, you could say something like, if I double the mass, then I expect the period to also double. Or I expect the period to be 4 times as big, or I expect it to be half as big, or some quantitative relationship like that should be in your prediction. Okay. Then you do the experiment. These are the basic instructions that I've given you. What you should be doing is writing this out step by step. So your experimental instructions section may begin with, like, preliminary considerations. Gather the following equipment. I need a stopwatch of some sort. I need a spring. I need some water to make masses and a measuring cup, that kind of stuff. And then measure the spring constant for the spring. Parenthetically, you can say we did this in a previous lab. And then step-by-step instructions. Okay, I've hung this much mass from this spring, and then I displace it by 2 centimeters or whatever. I then time it for 10 oscillations. Then I displaced it for 4 centimeters and time it again for 10 oscillations. Be explicit like that. Then say, okay, now we go back to 4 centimeters each time, but now I'm changing the mass, and explain how you do that. Okay, that's your experimental instructions part. Then you have your methodology. Experimental design is basically your instructions. Your results would be any data tables you've made, which here I have made a data table. Here is a data table with actual data taken on the 3 springs that I showed you. It's actually 3 data tables labeled by what spring we're using. You can copy from Excel into your Word document or whatever you're writing this up into. You can also just make a table directly in the document and write the numbers that are relevant in there. You can, let me open up a Word document here. Again, I like to use LibreOffice, but you're probably using Microsoft or whatever Mac's equivalent suite is. I think there's a Word suite on there. If I wanted to put in a table, I can actually copy the table. So copy, and then come over into my Word document, and this is a table. Like, you should have something other than just this is a table, and then paste it in here like so. And I've pasted my table. I maybe will anchor it as a character so that I know where it is. Insert a caption, figure 1, figure 1, call it a simple plot of spring force versus amount of stretch for 3 different springs. You can do something like that to add caption to it. And if you would like to change the caption after you've written it, it's editable, that kind of thing. Write a little caption. This can be, whatever, blah, 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 whatever you feel like you need to say here. Notice that this is single space, that's fine. But then when you're writing the rest, here's the body text, should be double spaced so that there are blank spaces between each line of text entered in the report body. Okay, so right now it's single spaced. Change this so that it is double spaced. So let's go to paragraph style here and go to double spaced like this. Okay, and so you should end up with something like this. Proofread it, make sure that you've got correct spelling, grammar, syntax, that kind of thing. And then at the end, you're supposed to electronically submit it. You need to turn it into a PDF file. You can export it as a PDF from Word or from LibreOffice Writer, and then upload it. Okay, I have in this handout given you an example of a table with some caption for it. I've given you an example of a graph with some caption for that. Basically, this section is your tables and your graphs. All right, in the discussion section of your lab write-up, what you're basically doing is now looking back at the data from the previous section, especially your graphs, um, and looking back at the predictions that you made back here in the introduction, um, and essentially discussing those two things with each other. So, or comparing and contrasting them, if you will. So if, for example, you made a prediction in the introduction that says, I think that the period of oscillation depends on mass and mass alone, but not the other two things. Okay, and you've shown your equation that shows why it is that it's only on mass. And then you look at your data and it turns out that, gee, when I plotted displacement versus period, I got the horizontal line. And when I plotted mass versus period, I ended up getting a curve or a line of some sort that was clearly not a horizontal line. And then when I plotted the second uh, spring over the first one, the two basically are just on top of each other. So if it's a line, they're both lined up like this, not like this. Okay. Then you'd basically cite that and say, okay, my prediction is correct, and then maybe do a little bit of error analysis and so on. You know, why did this deviate from a line if I predicted a line or whatever. Okay. The other thing is that you should compare the other quantitative prediction to what your data is showing. In other words, if you said, when I double the spring constant, the period will also double, then you should be able to point back to your data and show that, yes, when I've doubled my period, doubled my spring constant, the period did in fact double. I would recommend that maybe you measure what the spring constant is for your spring as is, which you've already should have done, and then measure it a second time where you have held part of the spring so that it doesn't all stretch, right? So like here's the whole spring and it can stretch this much, and here's half the spring and it can stretch, half the spring stretches. So measure what the effective spring constant is in each of those two cases. And that way you know, are you actually able to double your spring constant? Is it a factor of 2? Is it a factor of 3? Is it a factor of 1.5? So that when you go to make your prediction, you say, all right, I've got a spring that has a constant of, let's say, 30 and another one that's 40. So I expect the one that has 30 to have 3/4 of the period of the one with 40, or whatever relationship you predict. Okay. So that is what this section is for. Finally, you have to write a conclusion. This will summarize your results, talk about the validity of your experiment, whether there's any kind of substantial error or inconsistency, suggest possible further work. What else can you do with this experiment? Maybe you have only one spring available, and so you only do like full spring and half spring stretch, and what could you do in addition to or instead of that to maybe improve the experiment would be something you could talk about. All right. Finally, I'm supposed to grade you on writing quality. Basically, your figures are properly labeled and captioned, and plots have the appropriate titles, legends, axes, labels, units, all that stuff. You are using relevant terminology and vocabulary. So, maybe you introduce the word period, you define it, you introduce the word frequency, you define it, and then thereafter you just use the word period and use the word frequency rather than doing like a circumlocution with the definition. Okay. You should be checking for spelling and grammar and syntax as well. All right, so that is the set of requirements, and that is my walkthrough for this week's lab. Best of luck to everybody, and be sure to finally submit these PDFs electronically to me at the end. Thank you.